Hi, my name is Alceu, and I'm a PhD student at University of Campinas, and this is our work called Debiasing Skin Lesion Datasets and Models Not So Fast. Dermatologists' diagnosis is based on patterns present on skin lesions. We show some examples in this slide. In the left, we have dermoscopic attributes such as pigment network, and in the right, other features that can aid specialist analysis such as asymmetry and diameter. Learning these features would improve our deep learning model's generalization, which is key for the deployment of our solutions. However, in our previous work presented in the same workshop last year, we showed that the networks can achieve high performance even in highly disturbed scenarios. We evaluate the network's performance when training and testing with 4 versions of the data: traditional, where the data is unchanged; only skin, where we apply the segmentation mask to the image, removing the lesion out of it; bounding box, where we place a bounding box on top of the lesion, removing the information regarding the border; and finally bounding box 70, where the bounding box placed on top of the lesion occupy at least 70% of the pixels of the image. Even in this condition, bounding box 70 can achieve very high performance, and it was shocking to see it even when most of the image's parts are occluded. At that time, we asked ourselves what features are being used by the network, and our initial guess was that the presence of some artifacts, that are introduced during the image acquisition process, were the actual culprits for the shockingly high AUCs. So the objective of this work is we try to make sense of those learning process, and for that we annotate our images, the ISIC 2018 Task 1 and 2 dataset, regarding 7 visual artifacts that we think can lead to dataset bias. We evaluate how those artifacts can affect classification models, and we attempt bias removal in our skin lesion context. So, the suspect artifacts that we annotate our dataset are dark corners, hair, gel border, gel bubble, ruler, ink markings, and patches. Notice that multiple artifacts can occur in the same image. So, for example, in this image, there are ruler and also hair and dark corners artifacts present on it. All artifacts except for hair, they occur because of the acquisition process, and they are included in the images during it. The first thing we did was to evaluate the correlation, the Spearman correlation of such artifacts with respect to the diagnosis. And for our surprise, the correlation is not very high, which makes it unlikely for the network to exploit it. We also verified if the network can identify the presence of such artifacts in the dataset. So we trained individual networks for each one of those artifacts, trying to identify their presence or not in each image, and the performances were very high, achieving over 98% AUC in some cases. We also created normalized datasets where we remove the information from the background, putting in all the images from the dataset a single common background in an attempt to remove its influence to the result. The idea is that since most artifacts are on the background of the lesion, by doing this we are removing the bias. So when doing this, we can see that the most affected sets were bounding box and bounding box 70, where the AUC dropped by around 10 percentile points, in contrast to traditional and skin-only sets where they were affected by around 5 percentile points. Our explanation is that for those highly disturbed sets, bounding box and bounding box 70, the networks need to rely a lot more on these correlations, and because of that, when we take them off, the performances suffer much more. We also create some trap sets to intentionally mislead classifiers. So we create non-random splits to maximize artifact bias both on train and test, but with opposite correlations. So models that ignore artifacts should be unaffected by those in those training procedures, by those tests and training sets, but models that exploit those biases should fail catastrophically, and all tested models did. So this is an example of a train and test we did, and we can see very clearly that for train and test the correlations are opposite, but not only that, they were also amplified in comparison with the traditional set. We want to have a better idea of the features used by our models when diagnosing skin lesions. For that, we evaluate 3 models trained with different sets: traditional, normalized bounding box, and bounding box. The first column of each grid is the query, and the others are ranked according to the Euclidean distance between the image's features. For every row, we select a query image containing one suspect artifact. When observing the traditional grid, there are diverse features explored by the model, placing large lesions next to small ones, and also mixing artifacts a little bit. For example, in the first row, we can see there are other artifacts in the middle of the dark corner row, and also in the 5th one, we can see lesions of different sizes and also images without ink markings in this row. For bounding box, artifacts presence and lesion size and positioning become a lot more important, and it's the base of the decision for the algorithm. When observing the original images, we see that in contrary to traditional and bounding box, normalized bounding box contain artifacts distributed throughout the whole grid, while also exploiting sizes and positioning. In our debiasing experiments, we evaluated the method called learning not to learn, which is the state-of-the-art for debiasing, but it wasn't previously tested on a real scenario problem, and it works like this. In the first step, we train a feature extractor with a classification head for the main task, which is in our case lesion diagnosis, and the feedback from the lesion diagnosis helps the feature extractor to extract more relevant features for this task. In a second phase, we have classification heads for each one of our artifacts, the annotated artifacts, and we train these classification heads to excel at their job, but the feedback they give to the feature extractor is negated in a way to discourage the feature extractor to extract better features that help them. So this is the training procedure, and the intuition is that the extractor won't contain features to help the bias classification heads, only improving the lesion diagnosis without taking information regarding the bias. Here we present our results. We compare the performance of unchanged training procedure, training with normalized background images, and learning not to learn. The top part of this table contain our experiment with deeper networks, while the bottom part shallower networks. The trap test column is evaluating the capability of these solutions to work with highly biased scenarios, while Atlas Dermatoscopic and Atlas Clinical are measuring the generalization capabilities of this solution. We can see that all our models failed to work in this highly biased scenario, where train and test contain opposite correlations, but we can see that learning not to learn actually improved a little bit the result, especially for Atlas Clinical, which may show a hint that the biasing methods can help generalization and may become a common practice in the future. So in this work, we showed that traditional models are less biased than previously thought, even though they are still biased. We showed that the biasing methods struggle to deal with the skin cancer scenario, and that we need to advance a lot in this sense, in this area. And we think that domain adaptation, representation learning, and disentanglement can play a big part for it, so we can build more robust classifiers that can be applied in the real world. Thank you for your attention. For more details, please check our paper, and also we make available our code and our data through this QR code.